welcome back. In this video, we are going to discuss about the locating numbers of a graph G. So, before going to introduce what do you mean by locating number, let us start with an example. Suppose I have a complex that has 5 rooms R1, R2, R3, R4 and R5. Now, for the purpose of security, I have to place a sensor in any one of these rooms so that sensor has to send a message to control room if anything happens in that rooms. Suppose any fire cases happens in any one of these room, that has to send a message to control room. Now, to send a message to control room, that has to identify in which room the fire has happened. So that for that purpose we will assign a code to each room. For that code we use the distance from that room to another vertex as code. Suppose I will place, for example, sensor in this room. Now I have to give a code to these rooms, remaining rooms, so that the sensor uses that code to send a message to control room. So fire has happened in this room. So what the code I am going to use, as I said, that is the distance. Now the distance from R1 to R2 is 1. So the code for R2 is 1. Similarly for R3 the distance is 2. So the code for R3 is 2. The code for R1 is 2. The code for R5 is 1. And code for R1 itself is 0. Now if fire happens in R3 or R1, then it sends a message the fire has happened in a room at a distance 0 or 2. So these two are not problematic, but these three creates a problem, because if I receive a code or a message from the sensor that the fire has happened in a room at a distance 1, then it may be a R2 or R5 or R4. Identifying that 3 room will be difficult. So with the help of only one sensor, I can't determine exactly in which room the fire has happened. For that, I have to use one more sensor. For example, for time being, assume the second sensor is placed in R2. So here I use one more sensor. ಸೊ ಒಂದು ಸೆನ್ಸರ್ ಇಟ್ಕೊಂಡು ರೂಮ್ದು ಲೊಕೇಶನ್ ಅನ್ನು ಎಕ್ಸಾಕ್ಟ್ ಆಗಿ ಕಂಡುಹಿಡಿಯೋದಕ್ಕೆ ಆಗಲಿಲ್ಲ. ಸೊ ಅದಕ್ಕೆ ಏನು ಮಾಡ್ತಿದ್ದೀನಿ, ಇನ್ನೊಂದು ಸೆನ್ಸರ್ ಯೂಸ್ ಮಾಡ್ಕೊತಾ ಇದ್ದೀನಿ. ಸೊ 2 ಸೆನ್ಸರ್ ಯೂಸ್ ಮಾಡಿ ಲೊಕೇಶನ್ ಎಕ್ಸಾಕ್ಟ್ ಕಂಡುಹಿಡಿಯೋಕ್ಕಾಗುತ್ತಾ ನೋಡೋಣ. ನಾ ಅಗೇನ್ ಐ ಹ್ಯಾವ್ ಟು ಅಸೈನ್ ಎ ಕೋಡ್ ಟು ಈಚ್ ರೂಮ್. ನಾ R1, so I'll write a code such that in this form I'll write a code. Or okay, distance of So I'll write a code like this, x comma y, where this denotes the distance of that room to R1 and the second number denotes the distance of that room to R2. So here the code will be 0 comma 1 and the code here will be 1 comma 0. The code for room R3 is the distance from R1 to R3 is 2, distance from R2 to R3 is 1, so 2 comma 1, and it will be 1 comma 2, and it will be 1 comma 1. Yes. Now each room has distinct code. If any message received at a control room, so that the fire has happened in a room at a distance, any of this code, I can easily identify which room that has happened. So only case is if 2 rooms have same code, then it will be a problem. Now using 2 sensors, I can exactly identify the location of the room. Same idea we are going to use in the case of graphs. Suppose, okay, now let G be any graph. I'll write here, let G be any graph. I'll take a set of vertices, W equal to say W1, W2, W3 and so on, Wk. I have taken a subset of vertices. Now for each vertex of the graph, I'll assign a code CW of V, where V is any vertex in the graph, distance of V to W1, distance of V to W2, and so on, distance of V to WK. This is called locating code or simply code. So, given a graph, given a complex, I am taking some set of vertices, just like I considered R1 here to place a sensor. Then I have to assign a code to each of the vertex in the graph, just like I assign code to each room. So that code will be distance of the vertex to each vertices of W. So distance of V to W1, distance of V to W2, and so on, distance of V to WK. This is called code or locating code. So I have to assign code to each vertex. Now this is called a subset of vertices, and it is called a locating set if each vertices of the graph has different locating code. Otherwise it is not called a locating set. So W is called, this is called locating set if each vertices has different code, has a distinct code. If any two vertices have same code, then it's of no use. Then it is not called a locating code. If each vertices of the graph have different code, then we call W is a locating set. So given a graph, it may have any number of locating sets. So it will take a locating set of least cardinality. So any locating set of least cardinality is called, the cardinality of any locating set having minimum number of vertices is called locating number. So you have to take the locating set of all sizes, then you have to choose the locating set of minimum size or minimum order. The cardinality of such locating set is called the location number of G. So the minimum cardinality, minimum order or cardinality of a locating set is called locating number. Denoted by LOC of G. So this is the definition of locating number. Now suppose I draw a graphical representation or a graph representation of this complex. Then the rooms are represented by vertices V1, V2, V3, V4, V1, V2, V3, V4, V5, V1, V2, V3, V4, V5. Same case or same discussion applies here. Suppose I'll take only V1 as locating set, then V2, V4, V5 get same code, again 1, 1, 1. That will be a problem. If I take V1, V2, then you get different codes. Or for example, suppose I take V4 and V3. Suppose W equal to V4, V3 or V3, V4 you can take. Now let us identify locating code. This one. So this as distance 2 from V3, so 2, 1. This will get locating code 1, 2. This gets locating code 0, 1. This gets locating code 1, 0. This gets locating code 1, 1. So each vertex has got different codes. So easily you can say that the set W4, W3 W4 comma W3 or W3 comma W4 will be a locating set. Similarly, you take three vertices V4, V5, V3. Suppose W equal to V3, V4, V5. Now let us see whether it will be a locating set. Easily you can check that each vertices get different codes now. Now the code of V1 will be distance from V3 is 2. So distance from V3 is 2. Distance from V4 and V5 is 1 1. And this gets code 1 2 1. This gets code 0 1 1. This gets code 1 0 1. This gets code 1 1 0. See, each vertices have different codes. So W equal to V3, V4, V5. That is also a locating set. This as size 2 or cardinality 2. This as cardinality 3. So we take the location number of G equal to the minimum cardinality. Location number of G equal to cardinality minimum 2. So that's about locating number of G. Suppose if you see few more examples on this. First we'll consider a path graph. We know how to draw a path graph. So generally I take Pn. So this has say 1, 2, 3, 4 and so on up to Pn. Okay, n it is. So it is V1, vertex V1, vertex V2, V3, V4 and so on Vn. So this is a path graph on n vertices. Now I take W equal to I take first vertex V1. W equal to V1. Now I need to find, actually my intention is to find the location number of Pn. What is location number of Pn? This is my intention. What is the location number of Pn? That we need to determine actually. I have taken W equal to V1. Okay. Now I have to assign a code. So the distance from V1 to V2 is 1. Distance from V1 to V3 is 2. Distance from V1 to V4 is 3. If you continue in this way, distance from V1 to Vn is n minus 1. Distance from V1 to V1 itself is 0. See, each vertex has got different codes. Therefore, location W will be a locating set. W will be a locating set because each vertices in the graph got different codes. Therefore, location number of Pn is 1. Location number of Pn is 1. N may be any number. Next, let us take a cycle. That is example 1. Next, example 2. Let us take a cycle. Cycle Cn I will take. Cn will take 1, 2, 3, 4, 5, 6, 7, 8. So V1, V2, V3, V4, V5, V6, do one thing. Vn, Vn minus 1 and so on. So this is a cycle of order n. Now suppose I take again W equal to V1 only. Let us see what happens. If I take W equal to V1, then V2 gets code 1 and Vn also gets code 1. So two vertices are getting same code. That is the problem. So we have to use at least two vertices. Only one vertex is not enough to exactly identify the location of vertices, remaining vertices. So single vertex set is not a locating set. So this is not a locating set. Suppose I take W equal to V1, V2. W equal to V1, V2. Next, let us identify the codes. So this gets, the vertex V1 gets the code 0, 1 for V1. This gets 1, 0. This gets 2, 1, 3, 2, 4, 3, 5, 4, and obviously this will be 6, 5, and so on. So here distance of Vn from V1 and V2. So this as distance V1 in the distance 1 is there. So right here V1 1, 2, and similarly here this as distance 2, 3, and so on. This process will continue. And definitely you can check each vertex get different codes. Each vertex get different codes. So the set W equal to V1, V2 will be a locating set. Locating set. And if you take any other locating set that may have cardinality or size at least 2, either it will be 2 or greater than 2. 1 is not possible. So if you take any single vertex, that will not be a locating set. Therefore, location number of Cn is 2. Next, I will consider one more example. Example 3. Complete graph. Complete graph. For example, let us take K3. Let us take K3. V1, V2, V3. Similarly, let us take K4. V1, V2, V3, V4. Now, if you take a single vertex V1, then these two will get code 1. If you take single vertex in the case of complete graph, then each remaining vertices, each of the vertices will get code only 1, because in a complete graph the distance between any two vertices is 1. So singleton vertex is not possible because we get 1, 1. That is not possible. So I have to take at least 2 vertices now. Now I have to take at least 2 vertices. V1, V2, for example, I will take, then this gets code 0, 1, this gets code 1, 0, this gets code 1, 1. So in this case, the location number is 2. In the case of K3, complete graph on 3 vertices, the location number is 2. Now let's come to this one. Suppose you take only 2 vertices, V1, V2. One vertex is not possible anyway. So suppose I take V1 and V2, then this gets code 1, 1. Because the distance of V1 to V4 is 1, distance of V2, V4 is also 1. Then it gets code 1, 1. This also gets 1, 1. So 2 vertices, if you take any 2 vertices in K4, that will not be a locating set. Suppose you take 3 vertices. You take 3 vertices. Then the locating code of this will be 0, 1, 1. This will have locating code 1, 0, 1. This will have 1, 1, 0, and this will have 1, 1. So each vertices have different locating code or simply code. So this has location number 3. Similarly, if you take K5, in that case you have to take 4 vertices minimum. That will be a locating code. So the locating code of location number of Kn, the complete graph is n minus 1. So, so this is the procedure to find the locating number of the graph G. So similarly, try to find the locating code of other standard graphs. You can use, can consider complete bipartite graph, a star graph, pi-star graph, and wheel graph. So try to find the locating number of these graphs. Next, union of two graphs. Suppose you have two graphs, say G1 and G2. Now, say I have G1 equal to K1, say, and G2 equal to K5. I take this K2. K2 will be real. So this is K2 and this one K5. This is K5. Now the union of these two graphs is denoted by G1 union G2. G1 union G2. And it is given by just you have to write the graphs together. That's all. Just write the graphs together, nothing else. So this is now considered as single graph. G dash, G, or just take G. G equal to G1 union G2. ಇಲ್ಲಿ ಎರಡು ಗ್ರಾಫ್ ಅಂತ ಟ್ರೀಟ್ ಮಾಡಿದ್ವಿ, ಇಲ್ಲಿ ಎರಡನ್ನು ಒಟ್ಟಿಗೆ ಬರೆದು ಒಂದೇ ಗ್ರಾಫ್ ಅಂತ ಟ್ರೀಟ್ ಮಾಡ್ತೀವಿ ಅಷ್ಟೇ. ಸೊ ದಟ್ಸ್ ಅಬೌಟ್ union of two graphs. And there is one more operation, sum of two graphs, join or sum. Join or sum of two graphs. So sum of two graphs means again you have to write two graphs together. So I'll take another graphs. So P2 and P3 I'll take. To explain the sum, I'll take P2 and P3. This is P2 and this one is P3. Their sum P1 plus P2 plus P3, or the different notation for sum is this one. P1 join, P2 join P3 is given by, take this vertex, one vertex, and join this one vertex to each vertex of other graph. And take another vertex, join this vertex to each vertex of another. So that is about the sum of two graphs. Each vertex of one graph should be adjacent to every vertex of other graph. So that is about join. This is about union of two graphs.